All right, we're going to take a look at Coulomb's law. Coulomb's law is a force law, and it is the force between two point charges. When we say point charge, we mean literally two charges that are small and can be considered points. And what I'm writing up here is Coulomb's law. The K is a constant, and K is 9 times 10 to the 9 Newton meters squared per Coulomb squared. This is a universal constant, so it never changes in the formula. One thing is that sometimes this K is written a little differently. It's written like this in terms of a different constant. It's 1 over 4 pi times what we call epsilon naught. And epsilon naught is an important electrical constant. It's called the permittivity of free space, and it has a value of 8.85 times 10 to the negative 12 Coulomb squared per Newton meters squared. Now, you can see why we would, if you actually take 1 over 4 pi times this number, you will get the number up here, 9 times 10 to the 9. Most of the time, we're going to just use this. It's a lot more convenient. But this number, epsilon naught, will come up again when we study capacitors later on. And it's actually the fundamental electrical constant. So occasionally, you will see the formula written with this in place of K out here. And don't panic. That's just another way of writing K, though not as common. Now, Q1 and Q2 are the size of the charges in coulombs. And one of the things that we should mention is that while force is a vector, 9 times out of 10, we're going to put this in absolute values and multiply them together and disregard the negatives. You can have negative charges, you can have positive charges. We're using Coulomb's law to find the magnitude of the force. And the direction, we'll use our common sense. Now, R is the distance between the charges in meters. So if I have charge 1 and charge 2, you'll have a distance between the two, which is R. Using this equation is pretty much a matter of putting the numbers in. Let's go ahead and do an example. Okay, in our first example, we're going to look at the forces in a hydrogen atom. So we're going to look at the force between an electron and a proton at a distance of about 5.3 times 10 to the negative 11 meters. That's very typical for a hydrogen atom. The charges are a proton and a neutron. Well, a proton is plus 1.6 times 10 to the negative 19. That's the elementary charge of all electrons and protons. The electron will be negative 1.6 times 10 to the negative 19 coulombs. Essentially, they're the same. Finally, we're going to find the force. So the force is going to be found using Coulomb's law. It'll be K times Q1 times Q2 over R squared. So let's just plug the numbers in. I'm going to do it down here. So we'll have K, which is 9 times 10 to the 9. And I'm not going to put the units in for that. That's too much trouble. And then I've got 1.6 times 10 to the negative 19 times 1.6 times 10 to the negative 19, which I think I can just write as 1.6 times 10 to the negative 19 squared all over my distance squared, which is 5.3 times 10 to the negative 11 meters squared. If I plug all these numbers into the calculator, I'm going to come up with 8.2 times 10 to the negative 8 newtons. If the question came up, what kind of force is this? Is this an attractive or a repulsive force? Well, they're opposite charges. and so that must be an attractive force. Let's do another example. We have 3 charges here, all in a line, and what we're supposed to find is what the net force is on the charge in the middle. Again, we have to remember forces are vectors, so the direction and the magnitude are going to be important when we determine this. So what I would like to do first is determine the direction of these forces. So when I think about this plus 6 microcoulomb charge here and this plus 1.5 microcoulomb charge here, it occurs to me that they repulse each other. So the 6 microcoulomb charge is going to push to the right onto the 1.50 microcoulomb charge. Now the negative 2 microcoulomb charge is going to attract that positive charge. So what I'm expecting to see is a force to the right. So it looks to me like both of these forces are going to be to the right. So once I figure out what their magnitudes are, I'll add them together to get the net force. So let's go ahead and do the first one. So in the first one, we have 9 times 10 to the 9. Now we have to put in the charges. I have 6 times 10 to the negative 6 coulombs. That's a microcoulomb. And 1.5 times 10 to the negative 6 coulombs. Now the distances, whoa, I've got 3 centimeters, and that would be 3 times 10 to the negative 2 meters. And yes, you have to do lots of conversions in these problems. So we'll go ahead and put this in the calculator and see what we get. I come up with 90 newtons. Let's do the second one. We're going to have 9 times 10 to the 9. The 2 charges are 1.5 times 10 to the negative 6. It's the one in the middle. And the one on the right is 2 times 10 to the negative 6. And the negative does not matter. The fact that it's negative 2 doesn't matter in terms of finding the magnitude. We already determined the direction was going to be to the right. Now this distance is 2 times 10 to the negative 2 meters. Don't forget to square it, most common mistake. And let's see what the answer comes out to. Looks like we have 67.5 newtons. And let's go ahead and sum those up down here. The net force is going to be equal to 90 newtons plus 67.5 newtons for a grand total of 150. Well, if we round off, we'll get 158 newtons to the right. And again, all vectors have directions and forces are vectors. Right? Net force. There we go. You will come across problems where you will have charges lined up like this, where you might have charges not in a line. And in the case of problems like that, you're going to have to do all the nasty vector math that I know you all hate. You might have to break down some of these forces into components. If you had, let's say for instance, a positive and a positive and a positive, and you wanted to find the force on the bottom right charge, these two will repel each other, and you're going to have a force that goes off like this and another force that goes off like this. You will have to break down that diagonal force into components. It's just part of what you have to do, and you may have to figure out some angles using some trig if that's necessary. So it's tedious. I won't make you do many of them, but it's something that has to be done.